So great. So welcome back, everyone. So sorry for the slow start. The mirroring was not working as I was intended. Is it showing up there? Fine. Yeah. Okay. So I don't. I was going to try not to print out my notes today and have them on my screen, but this did not work. So I'm going to give the lecture without my notes. So we'll hope everything goes fine. So okay. So just I want to review a couple things about the stuff on the webpage. We've now had kind of a somewhat proper lecture. I want to point out that if you click on here, it will open up a page with the notes on it, which are more carefully done, and you can find for pretty good resources for each of the lectures. This one, the one today, is one I wrote recently, so it's not quite as polished. And then also, if you click on the S inside there, you'll get the slides that I wrote on the iPad for the day. So all that you can find on here. And if you click on the V, you will get the YouTube recording as well, or someone balancing on some rock someplace. Okay. Hopefully it points to my recording and not that one. Or it's possible that one's just as interesting. Okay. So then the homework, the statistical principles homework is posted. I see a lot of good discussion on the Canvas discussion board. If you haven't looked there already, there's I think some good questions with some fairly kind of reasonable kind of challenges that people are facing in the class, and hopefully I've been providing the right level of answers on all those things. If you have questions, especially technical questions, how do I actually get this implemented? The TAs have 3 office hours between now and the deadline to come, and so to help with that. Yeah, so hopefully the first assignment is going well and you've started to work on that. Any big questions on that before we get started? Great. So, okay. And then the other thing is the project proposal is coming up. That'll be due Wednesday next week. I have a bunch of posters that were made from previous semesters. I'll bring them in class on Wednesday, and then you can see some examples of things. But you should be talking with people trying to form groups. There's a Canvas thread on this as well as another way to do this. So that's hopefully a good way to find groups. But start thinking about that. You need groups and the project proposal. If you don't have a group by the project proposal due date and don't turn in stuff as you're supposed to, you will not get credit for that and will be forced to kind of arbitrarily group you together. You're better off trying to do this on your own, like before and after class, or using the Canvas discussion. Okay, let's get on with the lecture. Okay, so anomaly detection we'll talk about today. And this is a lecture that I kind of haven't taught this course since 2020, and I was thinking about what should be in the course, and it occurred to me like it was strange that we taught the course without including a lecture on this, and I feel like it's has to include this. So I probably, after you see the lecture today, I hope you think it's a fairly fundamental fundamental topic that probably has not shown up in your other courses. And you know what? I don't know if I ever took a course where there was a lecture on this either. I've been doing this in my research part of my life for a while, but I guess maybe didn't have the courage to say, okay, this is the fundamentally right way of doing this in the class, and right way to think about anomaly detection. Before we do that, I just want to review review from last time. We kind of went a little bit late on a couple of things. I wanted to make sure these were clear. We had a distribution, D kind of theta as we were calling it. And so this was uniform on values up to m, right? And you can simulate this with like a hash function. We talked a little bit about how to do that. You have to implement this for your homework. And we looked at two sort of events. Okay, it's the number of trials until a collision. And I just wanted to be clear that the kind of the median time for this was roughly square root 2m. Okay, we didn't really go through the analysis in class. It's in the lecture notes to explain how you get this. It's not the expected value. The kind of the straightforward analysis, the one that is common in this kind of this birthday paradox first collision example, gives you kind of the median time. When about half the times occur, that's roughly 2m, number of trials until you have a collision. Okay, and then we also had an event where this was where it's the number of trials until we kind of see all. So this first one we called the this is the birthday paradox, where you have two people with the same birthday in the same room somehow, and this is the coupon collectors. Okay, and I mentioned but didn't go through very extensively the expected number in this one is going to be roughly 0.577 plus log, and it's actually natural log of n times n, right? So roughly O of n times log n number of trials here. Okay, I just want to be clear because you use the question C in the homework, you're asked to compare to these things. Okay, and so I wanted to make sure that this is what you're comparing to. And that was one of the main takeaways. And maybe the number of trials until collision is maybe sooner than you thought. The number of trials until you saw them all was maybe faster than you thought, or maybe slower than you thought. The class was not really sure when we kind of voted beforehand. All right, so I just wanted to make sure that we have that clear. Okay, so now I want to talk about anomalies. And I think it's good to kind of keep that previous lecture in the background, because you're saying, okay, I saw I have a 10,000 slots, and after square root of 10,000, so that's about 200 trials, there was a collision. I saw two things collided. I have a hash table and I had a collision. Is this something anomalous? Should I be concerned about this, or is this standard? Right? Turns out that's about what you would expect. So the anomalies. What are an anomaly? And so you have to think. You have to know what to compare against to understand like an anomaly. Okay. So now let's try and formalize these ideas with some concepts, and we're going to think about data X as drawn from some sort of distribution again. Okay, and we're going to assume that this is IID. So actually X is equal to X1, X2 up to Xn, and each of these Xi's is drawn from the same distribution. They're all identical, the same distribution, independent. One draw does not affect the other draw. Okay, so we're going to assume this about our data. Okay, and this is kind of, we're going to assume we're going to collect data. We haven't necessarily collected it yet. Once we've collected it, it's got fixed values. But the model is assume we're going to collect data. How do we plan on what would be an anomaly if we saw it? Okay, So given, we have to make an assumption about what we would likely see. Kind of what is kind of so likely, or another way to think about this, and this is part of your data collection report for the project. So if we kind of have X, kind of how to generate, so similar X, okay? So I asked this question in the data collection report where we say, so you're going to have some data set that's going to be a fixed data set you've collected probably before you start the project, okay? And we want to think about how would you generate similar X, okay, if you were to generate this. And the idea is I want you to specify some distribution. What is the distribution you think is realistic that could have generated your data X? What is a model that data could have been drawn from? If you haven't thought about this when you're analyzing your data, you're not going to be able to say anything about something about, was there something unusual? Was there an interesting anomaly in the data or not? Because you don't know what to compare it to. Maybe if you generate the data, it looks exactly the same. It always has this one feature to it. You have to say, let me assume the data came from some property. Okay, we'll go through one simple change point example today to make this concrete, but let me try and lay the foundations about this before we start. Okay, so for anomalies, okay, we have to go through and think, one, so what is the kind of distribution of the data, okay? And this is not some answer I can tell by looking at the data necessarily. I have to model this. This is a model that you choose when you're saying, I think the data, I think the property, the world, it probably looks like this. And if it deviates from that, I want to know, okay? Then we have to say, what would an anomaly look like? Okay, and this has two properties to it. One is I'm going to need some sort of scoring function, and we're going to use something, we're going to call this a likelihood, or maybe a log likelihood ratio. Log likelihood ratio. Well, I'll talk about that. And second, I need some sort of shape. Okay, I need to say what structure could the anomaly have. I don't want to make this too open, or I'm going to end up on a fishing expedition. I'm going to see things in the data that are kind of that just because I'm looking too hard. You can kind of overfit to the data in some sense. Okay, and then I need to say, once I found it, I'd say how interesting. I need to somehow so I've got to, once I found where I think might be an anomaly, I need to somehow quantify, was that interesting or not? Okay, was this that unlikely, or is this just by random chance? I would expect to see collisions after roughly square root of m, of these different trials. How do I quantify this? Okay, and we need some sort of assumption on the distribution and the model in order to do any of this. You can't make a real judgment about an anomaly without some sort of underlying modeling assumptions here. Okay, and we'll throw a bunch of the rest of the course. We'll talk about specific scenarios where we take data. We'll start with the big example with text and drawn from like web pages and search engines, where how do we kind of take data and represent it in a way where we can do this. And we're going to do a simple one-dimensional change point example today in class. Um, okay, so let me start with likelihood. So I'm not going to try and formally define likelihood. Let me say informally, it's going to be kind of an unnormalized probability. But the probability depends on some sort of underlying assumption of the world, and the unnormalization has to be constant across all the ways you measure. It has to be a fixed unnormalization. I think the word likelihood is good because it maps to the common way it's used in English, in that it means that how likely is this to occur. It's a scoring function that's going to tell you how kind of the higher the score, the more expected this is. Okay, the formal technical definition I'm not going to go through, but we'll I may derive a simple example, or I may leave that to the notes, but it's going to be a scoring function on your data. Okay, and so what I want to think about is I'm going to have a scoring function on my data. I'll call this L, but it's going to depend on some sort of parameters. Okay. These are the parameters. So theta, these are the same parameters that I assumed my parameter is my distribution. Not all distributions are parameterizable, but let's just kind of simplify our life and think of them as parameters. And we'll go through an example where the parameters is just going to be a single value p, which is going to be like a real value. It's going to be kind of the center point of a one-dimensional sort of distribution. Okay, so we're going to measure a likelihood given a set of parameters. Okay, and then we're going to have an actually like a potential anomaly. Okay, a potential anomaly, and for now we'll call this S as a subset of X. Okay, so we're going to think of having some data. Remember, our data X, we're going to think of this as being these points here. This is our X here. And then we'll have a subset of this, maybe these points here. We'll call these points S. This will be a subset of our data X. Okay, and this is our potential anomaly. We want to kind of give a score to this possible anomaly. Okay, and what we'll do is we'll again, we're going to again define a likelihood of the anomaly. And this is just another scoring function. And this will be X, but it will also depend on kind of, sorry, let's not say S here, but it'll be like the likelihood of the anomaly, and we'll probably look at the data not in the anomaly. So X minus S is everything else, right? So this part here, this is X set minus S, okay? But we also need some parameters here. Okay, and I've given theta prime here because often if we're modeling the anomalous distribution, we're saying, well, something else is going on here. There's something happening in the anomalous space and something happening the other part. So this is going to be more complicated, okay? And so in this example, we'll say theta prime is going to be P prime and Q prime. Okay, there are going to be two parameters here, and these are both going to be just these real values. Okay. Okay, so finally, we're going to get our final score function. Our scoring function on the anomaly is not just going to be the likelihood of the anomaly by itself, but we're going to measure this with respect to the original data. Okay, and the typical way you do this is called a log likelihood, so ratio, okay, LLR, and I'll just write SX as shorthand, and this will be the likelihood. It's just a ratio between the likelihood of the anomaly with the parameters prime divided by the likelihood of the data. Okay, it's kind of, the notation starting to get a little bit heavy, but I don't want this to be too complicated. We'll go through an example here. And so it's going to look at the ratio of the likelihood to the likelihood of the what we think is the anomaly model versus that of the original model. Okay, so what's going to happen is for any choice of anomaly, right, what do we notice is that the original likelihood, this one does not depend on the choice of anomaly, right? So that means this denominator here is fixed with respect to S. So I'm dividing kind of by a constant, so it doesn't really matter. Oh, the log, like I forgot the log part here. It's the log of this. Okay, so it's a log of the likelihood ratio. Okay, so still this is not going to matter, right? The log means that I can take the log of the numerator minus the log of the denominator, and I'm subtracting a constant. So kind of there's a score minus a constant, but this log, if I can actually calculate the log likelihood ratio, this kind of tells me something about like a p-value sort of automatically. It feeds directly into all the world of statistics. It's kind of the right full way to measure. If we want to optimize this, we may not really need the denominator, but I just want to write it out. So there's some scoring function, okay, and it depends on the baseline. So the big takeaways from this before we go into an example is that there's some scoring function you can define for how interesting an anomaly is. Okay, and it depends on the underlying distribution of the data, that the assumed distribution of the data. You need to make an assumption on it, and if you change that assumption, it's going to change the scoring function. Okay, so we need to specify this in some way, otherwise we can't make a judgment on if it's anomalous or not. Okay, let me go through an example of this in Actin. Okay, and we'll talk about a change point. So detection. Okay. So now our data X is going to be a sequence of n, let's say, real values. Okay, so what does this mean? Now I'm going to get X1, X2 up to Xn, but I'm not going to treat them just as a set anymore. The set means, if I just treat them as a set, it means the ordering does not really matter. Okay, so you could write it as kind of, typically if the order matters like a coordinate of a high-dimensional vector, you might write this with the rounded parentheses, right? This would be, give me a high-dimensional vector, but that's not what I'm going to do. Typically, if you have some ordered sequence, you use notation like this with these pointy brackets. So it kind of means that X1 comes before X2, comes before X3, and so on. Okay. And I have that each Xi is still going to be a real value here. Okay, so I'm going to think about this as kind of, there's this ordering, and this could be like time going forward. I'm making observations, but I'm still assuming these are IID observations. Okay, so each one I'm assuming is from the same distribution, right? So I'm still assuming that Xi are IID from some distribution. Okay, and these values might be like this, right? So there's some value here. This is the real numbers. Okay, so these could be things like the kind of I'm reading the temperature over time. These could be the price of the stock, right? It could be the amount, the power used, right? So in a lot of power systems or solar powered today, or your charging your car, you're measuring how much power is being used by your house, right? So this is happening over time. And what we're interested in is there a point T where this changes, this distribution changes. Okay, but the baseline distribution is that there is no change. Okay, so the baseline distribution, we're going to say that D is that there is no change. Okay, so they're all coming from the same distribution, right? That xi is iid from this d theta. And we're going to say the real values, and we're going to say that the mean is p, and that there's some normal, so noise. All right, so I won't totally specify what this means, but that there's some independent normal noise in each point, and maybe where I drew that black axis line was the mean value, right? And it deviated from that with some normal noise independent. Okay, so the random draw is that normal noise. Okay, and then we're going to say this anomalous distribution, theta prime. Okay, prime was too big. Okay, theta prime is that there's a change at time t. Okay, there's some time t, and so I'm going to say that for x1 up to xt, these are iid from some distribution. I'm going to call this d with parameter p prime, and that xt plus 1 up to xn are iid from distribution with q prime. Okay, where this is kind of the mean parameter of the distribution, right? So what this would say, well, maybe the data was drawn where initially there's some noise up to some time t, and then it drops and it's lower after time t. Okay, and I say, well, there's some sort of, this is different from the original distribution, and there's some anomalous region here. It's as simple anomalous region as I can come up with, just this one-sided kind of interval. I was drawing power. I had my car plugged in. I unplugged my car or it finished charging, and then the power drawn was much less, right? I can kind of detect these things, right? And so the power company can kind of measure and detect these things at your house by doing analysis on this. So these are kind of the two distributions here. Okay, is this it's making sense so far? Okay, so we have these two different, and we want to distinguish between them. Yeah, question. Q? So Q is the mean. This is asking, what is this Q here? And so this is this is the mean of xt. You're not going to be able to read that at that scale. Okay, this is the mean of xt plus 1 up to xn of those values, right? So this is the parameter of the distribution after the change point. So this is think of this first section as the anomalous region, and then this section as the non-anomalous region. You can imagine, and we'll talk about more complex regions, right? You could have an interval in the middle where it's different than everything outside, right? But too excited? Okay. But for now, it's just a simple, just at the beginning. Okay. Okay. Good. So let me maybe. Oh, question.
Yeah. So I guess the change point detection is when we observe like a shift in the mean at point t.
Yes, that's right. And so we want to say, okay, the next questions will be, how do we find that point t? And then how do we determine, okay, there's always going to be some point t that gives us the biggest change. And was that sufficiently different than what we would have expected? There's always going to be some point t, even if I had the blue data, the original data, there would still be some point t I could find that maximizes my log likelihood ratio I wrote down on the previous slide, or that form, which maybe I'll write down next. And so how do we determine, is that interesting? Okay. All right, maybe let me just derive a little bit about the likelihood L of x given theta equals p. Okay, so let me say that I can write down the probability of xi given theta equals pe. Okay, as like I said, it was a normal distribution. So it's 1 over square root 2 theta pi times x to the minus xi minus p squared divided by sigma squared, right? So this would be normal noise, right? Where that means that this p distribution, this was the real values, and I have some value p, and there's some sort of kind of normal distribution around p, and there's some sigma, which is roughly the bandwidth of this function. Yeah.
What's that sigma to the 2 in the square root?
Square root of 2 sigma, and then pi. I think this is the right normalizer. Again, my notes are trapped under this window I'm sharing here. And that sigma is going to be a parameter. As we'll see, the sigma parameter will not matter as long as it's fixed. Okay? And so this is the probability of observing any one thing, any one xi given p, right? So this is the probability in a yeah, but it's a continuous probability, right? So you can't evaluate at any point, but we're going to treat this as a likelihood, right? So we can write that the likelihood of xi given, so this p, right? So this is going to be kind of, in this case, I can write down it's going to be equal to theta equals p, but I can also write this thing so it's proportional to and this is write this a little better. This is a symbol, looks kind of like this, where I can ignore the leading coefficient. I'm going to obscure the normalization, this part here. This part I can kind of ignore as long as I'm consistent with it, and I won't be that careful with it in these lecture notes, but you can see it being more careful, in the notes online later. But I can say if this is proportional to x of minus xi minus p squared divided by sigma squared here. Okay. And now I want to write the likelihood of x given theta equals p. Now I have a data set, a full data set x. And I said these were independent, which means that this is going to be proportional to the product of I equals 1 up to n of, let me just skip to x of minus xi minus p squared divided by sigma squared, right? So now I'm indexing over the I of the data point, and I'm taking the product of all these, right? The joint probability, if they're independent, is the product of the individual probabilities, the same with likelihood. Okay. And now I'm going to look at the natural log of this likelihood. Sigma equals p, right? And now I can't quite do proportional to anymore, let me just write, this is the natural log of the product of I equals 1 to n of these x sigma squared. But what can I do with the product inside of the log? I can push this outside and turn this into a sum. So this is equal to the sum over xi to n of the natural log of the exponential of x minus xi minus p sigma squared. And the natural log and the exponential cancel with each other, right? So then this becomes negative 1 over sigma squared sum over xi to the n of xi minus p squared. Okay, so I've reduced this, the log of the likelihood, the natural log of the likelihood, ignoring these constant factors, which, if you trust me, aren't going to matter so much. I can reduce this to some constant, depends on the bandwidth times the sum of the squared errors. So sum of squared errors here, which you probably see all over the place, right? And the value of p, try to write this a bit better. Okay, the value of xi minus p squared, the value of p that optimizes this, right? So the opt at p equals 1 over n xi, right? So I can set the value that gives me the largest value. Remember, there's a negative in front here. So if I ignore the negative, then the smallest value, the smallest sum of squared errors, the largest negative sum of squared errors is the mean. The mean is what minimizes that. Okay, so if I have normal error, then I want to model this with the mean of the distribution. Okay, so shorthand. So if I'm going to write that the natural log of the likelihood of x given p under the assumptions of this model is going to be equals to negative 1 over sigma squared I equals 1 to n of xi minus p squared. Okay, and if I do a similar derivation, then for s and x set minus x with p prime and q prime, okay, the log of this is going to be the negative 1 over sigma squared, and then it's going to be the sum over I equals 1 to t of x minus xi minus, let's say the anomaly value is q prime squared plus I equals p plus 1 up to n of xi minus p squared. Okay, so I can say I'm going to fit the mean on the first part up to t with q prime and the mean on the leftover part with p prime here. Okay, so these are this is the value with the anomaly. It's a bit more complicated here, right? So again, we have our time and our real values. And then if we have data that looks kind of like this, okay, maybe we're going to say that for the baseline P, I'm going to fit a single value P that fits the same data, and there's going to be some sort of normal, assume some normal distribution here. Okay, whereas with the anomalous thing, I'm going to say there's a time t, and for here, I'm going to fit a value here. This is q prime is the mean, And again, there's some normal noise on top of it. And after time t, there's p prime. Okay, and so this is my value of the anomaly here, right? This region here is the anomalous region. Okay, so this is one model of anomaly detection. Okay, and if I look at the log likelihood ratio, I'm gonna be taking this, let's see, this value, and I'm gonna be trying to maximize this value, subtracting this value, the likelihood of the baseline distribution, right? The log likelihood, instead of the ratio, when I take the log, I do the first one, the anomalous log likelihood minus the original log likelihood. Okay, and this one does not depend on S. Okay. Okay, so now I could write this down. I can calculate this for a particular value t. If I gave you data, you could calculate this value, given values p and p prime and q prime. Okay, so there's one more step in order to get the value that I actually want. So my score, and we'll call this kind of gamma of S, is going to be the arg, not the argmax, just the max of p prime and q prime of the natural of the log of S x minus S p prime q prime, okay, minus max of p of log of xp, okay? So I want to choose the parameter value which maximizes that best fits the model. And in this case, it's basically a simple mean over the data I have.
Not need to do the log likelihood for the.
Yeah, it should be a log here. Thank you. Okay, yes. Okay. Okay, and it would, great. So I want this score. I'm going to just directly call this score. We'll just label this as the log likelihood ratio of Sx. Okay, so I want to max, this log likelihood ratio basically is going to be implicitly maximizing the values of p, p prime, and q. I'm going to fit them with the best fitting values. Okay. So, okay, great. So now, given a choice of anomaly, I can find the best. I can give this a score. Okay. So what's left to do? I need to now find S. We'll call this S star, which is going to be this one is going to be an arg max over S sub t, which maximizes the log likelihood ratio of S sub t of x. Okay, so now basically I'm searching for the value t, right, which will define my kind of anomaly, which kind of maximizes this function, right? So again, given this one-dimensional data, right, I need to search for some value t where this is now S of t here, which maximizes this value. So, okay. So in this case, again, I chose a simple example. So how would I search for this, right? So, well, what would you do to try and optimize this function? Some function I've written code that given a subset or a parameter t, I can compute this value LLR. Explained on the previous couple of slides how to compute it, right? It's a bunch of of sums of differences squared, basically. So how would I, given this, how would I find this anomaly ST? Why is it this one and not a different choice here? So how many choices do I have? Yep. Yeah, so I've got only n choices. This is great. There's a, you know, if I'm thinking about time, it's a continuous random variable, but I actually have only n observations, and it only matters what the subset is, right? So as I'm increasing the subset, the t only matters if it crosses over a boundary that includes another pointer. Great, so I only have n choices, so good. So should I compute all n values, just throw them all into my function? No, okay, then what?
Maybe you can use calculus to find the optimal t based off like the mean of all.
Yeah, can I use calculus and then take the derivative with respect to t of this? Yeah, you could kind of do something like it. It's not going to help you too much because you're not going to get a single, the value is going to be piecewise constant. So calculus won't help you too much. For any value t in this range, it's going to have the same value, and it will change when it crosses a point. Okay. Yeah.
You can do a binary search of t, splitting it in half. And then...
Yeah, I could try binary search. If you think binary search requires that the function you're looking at is going to be so unimodal, right? So it's got a minimum and it's going to be increasing, right? That there's some underlying function that if I drew LLR, these are good points to say that the function looks kind of like this, right? It doesn't have to be convex, but it has to be unimodal so that it's only decreasing until it hits t star. And so then you can actually do something called binary search, maybe not, but you can do golden section search. And this will allow you to define this with something like binary search. Yeah. Yeah, gradient descent requires convexity, and I don't quite have this. It's actually, I mean, this function is actually a step function, right? So I don't even have a derivative defined in. Yeah. Yeah, so I can kind of, okay, so you can start by saying, what if, right? So what if t is equal to 0, basically? And I can calculate the answer, right? I can say, okay, that means that everything, there's no anomaly, right? And then I say, well, what happens if t is equal to 1? Do I have to recompute everything or not, right? If I go back to these functions here, it's a sum, and it's this decomposable function that's the sum of things, right? If I change one point from being an anomaly, I don't have to recompute everything if I stored it carefully. I can look at the effect of that one point and move it from the first model into the second model. Okay, now to be a little bit careful, I need to have like a running average of the p's and the p prime and the q prime, but you can actually do this in constant time, right? So the trick is that going from LLR basically of 0 to LLR of t equals 1, this takes O of 1 time. So I can update this function in constant time by changing one point. And this is often the case because they're often decomposed as these sums, and you can often update them quickly. Okay, so this means I can start at one of these endpoints where the answer is simple, and then I can slide and work through, and I can calculate every value along the way. So I have to read all the data to calculate the first one, and then every update takes linear time, and the overall cost, so the overall time, so it's O of n time plus n times O of 1 time, and this is O of n. Okay, So this is maybe, and if they didn't come sorting, I may have had to sort them first, but maybe they came in sorted order, right? So I get O of n time to calculate the anomaly. I actually can evaluate every single one of those potential regions. And in this case, I can do it without I don't have to spend time to compute them. It's basically free if I'm careful how I maintain this as I sweep across. Okay. But I'm looking at every single region here. I cannot assume convexity to run gradient descent. I cannot even assume that it's unimodal, so I do this. This does not hold. This does not work. Okay, and this is typically the case. You could have local regions that might be a good anomaly or some other region that subsumes it, but is much bigger, that's slightly better. And I have to kind of check all these things. And this is often kind of unavoidable. Okay, we'll talk about some algorithms where that's maybe not the case, where you can find things, or maybe things where people kind of cheat and they say, I'm going to run this algorithm, it's going to work pretty well, and I'm going to assume that this is the best answer. Okay, we'll see these throughout the semester. But this is, again, a very simple example where I just check them all. And in the worst case, you kind of have to do this. Okay, this makes sense? Okay, so now, at this point, we've defined, or we've talked about, or defined in this example, an underlying assumption of what the data looks like. We defined an assumption of what the anomaly looked like in that space. It's this interval kind of region. And how to compute the likelihood for that. We can compute the log likelihood ratio, which is the score function we want to evaluate. And then we can find the best anomaly by trying all the possible shapes that define this anomaly. Okay, we found the one that has the best score. Okay, this is kind of limiting, right? Like, let's say my data looks like this. Again, I have kind of real values here, and let's say my data looks kind of like this here, and then there's some region where it's larger, and then it's smaller again. Okay, so what is the change point detection algorithm we talked about going to work here? I want to do something slightly different now, where I define my anomaly as this kind of subset, right? Where it has kind of a T1, or maybe it has kind of a start time and a terminal time, right? So it's an interval still, but it has a start and end. Now it's a two-sided interval, okay? But everything outside of it, I assume, is the baseline. Okay, this basically still works. It's just my family of anomalies is now more complicated, but the baseline, the likelihood, is defined the same way. I could also do this with, I assume they're going to be exactly two intervals, right, that I need to search over. Now that optimization of which anomaly maximizes this, the shape, is a bit harder. I could do it. Now I have to check all values of S and all values of T. There are n of these and n of these values. So there are n squared values I have to check. Okay, now there are n squared anomalies. S kind of ST, right? And I have to check all of them to see which one is the most anomalous under the log likelihood ratio, but I could do this. Okay. Okay, so in general, I can define, let's see, yeah, so let me kind of give a little, there's one more question we have to answer, but I want to generalize this just for one slide, just a little bit. We have to decide if what we found was actually interesting or not, right? Was it a region that was, this one looks pretty different, it's pretty obvious there's something going on here. Maybe this one, it's not as obvious. Maybe this is within the normal range of variation. Okay, how would I answer that question? But I first want to generalize this a little bit. I can have two, I want to say something that will generalize to these metric problems we're going to talk about later in the semester. I can think of two, so distributions of data, d theta of n and my d theta prime of n. Okay, so these means I've taken, actually I don't need the part n. Okay, so I've got these two distributions. Maybe this was my baseline. This is the baseline, and this is the anomalous. Okay, and the distributions may depend on and these distributions can be parameterized by maybe just P and Q. In the case we talked about before, they could be something else. Then I want to find a kind of way to measure, right? So these are going to generate, going to have data. So data coming from these two distributions, and I want a way to measure, and this will be called a range space. Okay, and so this R tells me the shape of the anomalies. Okay, so this could be negative infinity up to t. These are the one-sided intervals. This is the change point. It could be st. These are the two-sided intervals. Okay. It could be that x is in R2, and my range might be a circle that has a center and some radius. Okay, so this range could define all kind of the space of all balls. Okay. Okay, and so then I can define a distance between these two distributions, d of theta and d of theta prime, with respect to this way of measuring. Okay, and I'll define this as the supremum. You could think of it as a max of all ranges of all shapes, where I will want to measure the expected value of x in distribution 1 with the range on x minus the expected value of x prime in distribution d prime theta prime with the range x prime and this difference. So I want to find the range which has the most difference between these observations. Okay, this is called an integral probability metric. And if I define it this way, it's always going to be what's called a quasi-metric, which means it satisfies things like the triangle inequality. And if I'm careful about the range, it'll always be like a metric. We'll talk about these later in the semester, but this gives you a way of measuring a distance between probability distributions. And I can decide, is change point enough? Do I need two-sided intervals? Do I want to look at disks or rectangles in higher dimensions? That defines which choice of the metric here. And these are changes between kind of distributions, or distances between distributions that define nice kind of metric properties. Okay, so this was a little bit of an aside here. So for those of you, yeah. Okay, so this is integral. Yeah, sorry, I know my handwriting on this thing is not great. Okay, integral probability metric. If I write in the lighter font, can you all still see it fine? In the thinner font, should I stick with this? Maybe this will be, okay.
I just, what about beginning, you put CP?
This is the supremum. So if it's like a maximum, but it's over this, the space maybe may not have a limit. So you can just think of this as a max. Think of this as a max. Okay. So okay, so you take the max. So again, I want to find the range, that interval that maximizes the difference between the two distributions. Okay, this is defined on the expected value of the actual distributions, not the samples between them. I can take samples to approximate these expected values, right? And take the average over all the things, and it can be 1 if it's in the range and 0 if it's outside the range, for instance. Okay, that gives me the maximum, and this kind of recovers basically what I was doing before. You can think of it like this thing called the integral probability metric. We'll come back later in the semester to different distances between distributions or sets of points, and this will be kind of, might be useful. I don't expect you to fully understand all the things I said about this so far, but this will make sense in the context of things we'll see later in the semester. So it's kind of a preview. Think of this slide. Yeah. Yes, correct. I can use these two with either the one-sided or two-sided intervals, the change point, for any data that's ordered. I can define, it does not need to be the real values. Anything I can have a sort of order over, this is the valid metric of it. Yeah, it's a great observation, right? So if you can sort your data, you have a comparator operator, you can apply this to compare two distributions of items. Yeah, great. So if I have like names, right? Names, I can sort names lexicographically, alphabetically, right? And I don't really know what the distribution, there's not real values, but I can measure the distance between distributions of names in Utah versus elsewhere, which, no, Utah is a fairly unusual first names compared to the rest of the US population. Yeah. Yeah, so this is defined over the underlying continuous distributions, actually, and I can approximate this by drawing samples. If I don't have enough samples, I don't have a good approximation of the true underlying distribution. You can say, how many samples do I need? And it will be kind of, to get epsilon error for some like 1% error, I need 1 over epsilon squared number of samples. So to 1% error, I need about 100,000 samples. It's good to understand this. That seems like a lot. That's what you need. So 5% error is like 400 samples. So that's not so bad. And 10% error is about 100 samples. It also depends on the complexity of the range. And you can quantify this through the concept called VC dimension, which you may have learned in machine learning class. So the VC dimension also linearly with the VC dimension. So these are all, that's how many samples I need to be able to kind of approximate this distance. So this is useful to understand. If I want to compare the true distributions, I only get a sample to witness them from. Well, then how many samples do I need, right? This is what learning theory kind of, that same sort of kind of analysis applies in this setting as well. Yeah, okay, great. So let's pivot back to the last question I needed to answer, right? Okay, so I found S star, which is arg max S of my log likelihood ratio of S X. Okay. Is it interesting? Okay, is this interesting? So, okay, so is this interesting? So if I have a true log likelihood ratio, if I know, okay, so there are a bunch of different ways to answer this. Okay, the first one, if I totally trust kind of my models, d theta and d so theta prime, then the log likelihood ratio, then LLR tells me something directly like a p-value, right? It's like the t-score. I forget statistics. It's something like the t-score related to so p-values, right? So if I fully trust them all, I can look at the log likelihood ratio and I can say, if this is so approximately, if the log likelihood ratio is about 2, then the p-value, I think this, again, I think this corresponds with a p-value of roughly 0.05, right? So if it's larger than 2, I might think that this is interesting. If it's less than 2, then I think this is, I may have, and this may be the likelihood ratio. So but there's some direct correlation with like the p-values and fill hypothesis testing. Okay. Okay. So I don't always. So I can just look at the log likelihood ratio. If it's 1, they're equally likely, right? This could happen, for instance, if the anomaly is basically empty, right? So then the likelihood ratio of them should be about the same. The likelihood should be a little bit higher for the one with the anomaly because it's have P and Q. I have more parameters. I can fit the data a bit better. But if they're about the same, then I might as well just stick with the baseline distribution because it's simpler. But if they're more different, the ratio is roughly 2 or bigger, let's say, okay, I'm fitting the model sufficiently better. Okay. I typically don't trust the log likelihood ratio directly. Let me give you a couple of other answers, ways to do this. Sometimes you're just going to have a score function that the other thinking is like, what if LLR is just a kind of score? Okay, so in other points in class, I'm going to say, here's the function that we're optimizing. Okay, and we're going to try and optimize this. We're going to find the best way to fit data with this with this function to optimize this score. But I haven't really derived a log likelihood ratio directly. Sometimes you can do that underneath, but not always. Sometimes I just have a value, and I say this is the anomaly or the structure way of grouping the data that maximizes the score. Okay? And so I can't really trust the value. 2 isn't necessarily meaningful, right? Maybe the value is, I'm optimized it, but it's still negative or something like that. Okay, so here are a couple of other options. This second one is I can draw more data from my underlying distribution. Okay? So maybe I assume there's some way to generate data. For instance, when we get to the graphs part of the class, there'll be ways to generate random graphs from these like block models and so forth. And there are ways I won't be able to generate random graphs that have this sort of this block structure. Okay, so what I'm going to do is I'm going to draw x1, x2, up to xn. And I'm going to draw these all from this sort of distribution. Okay. Then I'm going to compute the score. We'll call this gamma of x1, and this will be a value gamma 1. And I'm going to get gamma 1, gamma 2, up to gamma n. Okay. And these are all this data sets I've drawn. These are kind of these sets. And then I'm going to compare my score gamma of X, which is my input, right? I'm going to compare this to this gamma 1 up to gamma n. And I say, and I'm going to kind of record what fraction of gamma 1 up through gamma n are greater than gamma x. Okay? And I say if, say, this fraction, kind of number greater divided by n, right, is less than, say, 0.05, then this is interesting. Okay? So this is a way of using simulation where I can generate more data sets, run the same algorithm again, compute the same score, and compare them to the value I calculated, my score. If my score is bigger than all of these or almost all of these, right, then they're less than 5% are bigger than mine, then maybe I say, okay, this is significant, and I would kind of reject the null hypothesis sort of thing, right? I can do this with simulation. I only have to trust the model, not my scoring function. I say the scoring function is what I'm going to use in order to measure this, and it doesn't need to be a log likelihood ratio. It could be, but it doesn't need to be. And then I can evaluate the significance of this anomaly effect just through simulation. And I don't need to use 0.05, it could be 0.01, could be 5.9, so 0.00001, right? Your choice. And in fact, it tells you something about how interesting is it against your distribution. And again, how big should n be, right? I need to choose n large enough, do enough simulations so I trust the answer, right? Again, I get about to epsilon error in this value, I need about 1/epsilon squared, right? So again, it's 10,000 simulations to get about 1% error in this kind of p-value proxy. Okay, I'm gonna give you one more thing to do. Okay, 3. What if I do not know the theta? Okay, so what if I kind of assume I want to assume as little as possible. What if, or if I don't know how to simulate new data? Okay, so one thing I can do instead is I'm going to permute existing data. Okay, so I'm gonna, this makes sense if I have one of these kind of subset defined anomalies where like the ordering matters. So I'm gonna take x1, x2 up to xn, and these are my data set x, and I'm going to randomly permute the order. Okay, now I'm going to get a new, maybe this new ordering is x7, x12, x3, and so right, and so on. And I'll call this x1, and then I repeat this again, x2 up to xn, repeat this n times. Okay? N times, I'm going to get n sets, and then I'm going to calculate n values. Gamma I equals gamma of xi again, right? And then I'm going to again compare my gamma of x to the distribution gamma 1, gamma 2 up to gamma n. And if it's bigger than all but 5% of it or all but 1% of it, I'm going to say assume that it's interesting, right? So this would be called a permutation test. Okay, so for this, I don't need to know very much about D, only that I assume that the observed data is drawn from the kind of the proper distribution, and that the ordering is what matters here. How I measure depends on the ordering. That I can just permute the data without even knowing the distribution, and I can kind of compute any score function and compare against the score function. Was it significantly interesting for this choice of the score function? Okay, so then this gives me a sense of how interesting are the anomalies with kind of less and less information. So kind of great. So we went through this framework. We will not see this probably through the rest of the semester as explicit as thinking about anomalies. But what we will see is how we're going to find certain structure in data. This is the best fitting structure of the data or the most similar data. We're going to say, how unusual is this? Sometimes I can derive a log likelihood ratio test and kind of calculate stuff exactly. Sometimes I need to use simulation or these permutation tests to evaluate this. Okay, and there are different ways of evaluating it. There are different ways of calculating these score of how interesting is this anomaly. They may not all give the same answer, right? It depends on, do I put a lot of faith into a model of the distribution? Do I try a permutation test? Do I have enough data points to trust this? These are all questions we're going to have to ask. And the modeling you do to set up the problem will determine the answer. Okay, so we're going to look at throughout the semester, I'm going to give you a large set of tools you can use to try and find and determine these structure and anomalies. And you're going to have to choose what's the best one for the data. And there's going to be some modeling involved. Which one do you choose? And that's going to think, okay, what is the data trying to look like? And which model fits with which algorithm, which gives you which answer. And it's not going to be so clean cut. Okay, great. Well, we'll stop here. Thanks.